This tutorial where we're going to use the Swift programming language, the NIO networking framework, to create a multi-user dungeon or MUD game server, something that you can run on your Mac or on Linux PC or Raspberry Pi on the cloud somewhere. So it will be a web application or networking application, to be more specific, that other players can connect to. We'll be using Telnet for now and hopefully enjoy our game. So we'll start first we need to start with the basics. So first up, we need to create a new project, and because this is going to be something that should also run on Linux systems, for instance from Docker containers or on a Raspberry Pi or an AWS server, the best way to create a project is to use the Swift package manager, because that's not dependent on Xcode itself. And to create a new project, you first create a new directory. Let's call our project NIO Swift MUD, and we'll enter the directory and then initialize a new project of a type executable. And this creates a couple of standard files, and the package.swift file contains your project definition, and that's the one that we can open. And once it's opened, it automatically opens Xcode, at least on the Mac. It takes a bit of time. There's Xcode, and let's see, we can make it a bit larger. So we have a project here, and this is our package file, and it's really empty yet. We also have a single Swift file that simply creates a hello world project. You can build and run it this time if you want to check whether at least the pipeline is complete. For now, what we're going to do is we're going to add the NIO framework, and the NIO framework can be found on GitHub. And this is the location, but I'll also put it in the description below. And what this is a highly performant cross-platform network application framework. So you can use this to create all sorts of network applications, and we're going to do the most basic type of interaction imaginable, but are really much more complex examples and improvements that offer TLS support or SSH and so on. Right now we're going to stick to Telnet because it will be complex enough as it is. So we need to get this project into our application, and the easiest way to do it is to go to code, copy the URL here, and then use Xcode to add the package. And there should be, luckily there's help. Add packages, and we'll just have to enter the URL here. We see with NIO, then we can choose what we want to do. Basically, I simply want the latest version somewhere between 2 and 3, and I'll add it. I'll copy the dependency. Then we'll use the old-fashioned way. So we have a URL. That's the one we call. It simply added it to. That's sort of nice. So apparently the UI window simply creates one of these tags. So and this should be the one, and it's already starting to download NIO in the background. And what we need to do is we also need to add it as a dependency to our target. So, and we're going to do that as a product. It's called NIO. The package is Swift NIO, and there's no condition here. And now we should be able to import NIO and get everything from it that we require. So how do we get started? Well, we first need to bootstrap a server, and that takes a couple of steps and a bit of boilerplate code, but I'll try and explain as we go along. So first thing we need an event loop group. And what's an event loop group? An event loop is sort of a thread specifically for NIO that's able to receive requests and process them. I think that's the easiest way of explaining it. And we'll make a multi-threaded application, and we'll use the amount of cores we have in our system as the number of threads. So that won't be too many. I think that would translate to 8 threads in this system, because it's 4-thread hyper-threading system, something like that. That might not seem like a lot of threads, but the NIO framework is designed around a concept called asynchronicity, and that means that it assumes that when a request comes in, comparatively little time is spent CPU bound processing, like performing calculations, so on, and most time will be spent doing IO work, or when you look at it from a thread, from a CPU thread count, waiting for IO. And it sort of makes sense, because CPUs of course are incredibly fast, and storage and network are also fast, but compared to a CPU they're extremely slow. And so it's a relative scale. So NIO is designed in such a way that once you find something that is more or less IO bound, that you free up the thread to do something else while waiting for the IO to finish. And once it's done, then it can continue where it left off. So it's really based around parallel processing, and it's based around asynchronous work. And it used to be quite difficult to program in Swift, because it required a nesting callback after callback after callback. And now we have macOS 12 and Swift 5.5, so of course we now have async await support, which will make this type of code much easier to reasonable with and much easier to write. So that's a nice reason to start working on this now. So we have our group of threads, and we can use that to create a server, at least bootstrap a server. And bootstrapping a server at least requires a group, but we want to do some additional configurations here. So we set a server channel option to at least set a backlog, and this makes sure that no more than 256 connection requests can be waiting at a time. So if for some reason the requests come in much faster than you're able to process them, we accept a waiting queue of about 256. In your own application, this might vary a lot, but I mean, I'm not expecting our simple MUD server to get even remotely close to this one. Then we set a socket option, and this one might be a bit more important, because here we're going to set to reuse address sockets. And this is required to be able to locally test your server, but also run multiple servers if required, run multiple telnet sessions. There's a lot of technicalities behind it, but for now, let's just accept that we need this one. So those are basic server configurations. Now we get to the more functional parts. We need to set up a pipeline. And a pipeline is more or less a definition of the route that a request takes before it's processed and a response is sent back. And Swift NIO uses that to defines a pipeline using handlers. And we can add them here. And the handlers are basically, they have an input side and an output side. The input side receives a request, does something to it, and then sends it away on the outbound side, where it's picked up by the next handler, all the way through until there are no further handlers, and the response is sent back to the caller. The first handler that we're going to add is a back pressure handler, and this one is built in. And what this one does is it protects our server from getting more data than it's able to send out. So it's sort of buffering, or it's basically protecting our server from overload. So it's a good one to have as a start. And for now, this is our only handler, because this is the only built-in one that we need. And all the other ones we will add momentarily. We're almost done with setting up the bootstrap. So we have our child channel, and we also need to set some options for the child channel. And also here we have our channel options. A socket option, this one as well needs to be set to reuse address. We have max message per read. This one tells how many messages a single read can process. This helps keep buffers within a reasonable size. And the final one is the receive allocator, and this one is quite important because this one tells how buffers are created in NIO. And internally, Swift NIO uses mostly byte buffers, so basically sequences of bytes to transfer data around. And this is pretty complex. This allocator is quite flexible because it allows resizing of buffers. So this makes it a lot less likely that, for instance, your buffer overflows. We have a channel in. Yeah. So most likely this error will go away in a bit. So we have our bootstrap. Now let's try and get a server up and running. So we need a host name. We'll use this is sort of the local host in IP6. You can also use local host. You can use whatever you want, an actual IP address, a host name, something that gets resolved. Be careful when you're using the wildcard one. That's quite useful when you start running this application server to connect from other systems, but you will get a warning when it's starting up, at least on macOS, not on other systems. And it's most likely a macOS bug, but still. I don't like seeing too many errors when running test software, so let's keep it at this. So we need a port, let's say a couple of 8s, and then we can create the server, and we'll do that by trying to bootstrap and bind our server to a host and a port, and we'll wait until it's done. And then we can print server started successfully. listening on address, and the channel has a local address. It's an optional, but I don't mind force on wrapping it here, because if for some reason this optional for the local address it doesn't have a valid value, then obviously something went wrong bootstrapping the server, and there's really no way of no reasonable way of continuing. So I prefer to then have the application crash in the most spectacular way. So we have a server, and then if we may need to make sure that it doesn't stop immediately, because hey, it's done running. So what we'll do is we'll wait until the channel itself is actually closed, and this will only happen programmatically, so using something we create ourselves, and then we can say print server closed. I think this should already run, even though it doesn't do that much, doesn't do anything really spectacular. So it says it's running. Let's get our terminal up. It says it's listening, so we should be able to telnet into a local host, and well, at least we're connected. But that's all there is. I mean, it's not doing anything, because the back pressure handler by itself doesn't do anything useful. So let's go one step further, and that will be the last step in this first episode. We're going to add an echo handler. The echo handler is the hello world of networking applications, and what it does is it simply echoes back everything it receives. So we create a new Swift file, echo handler, and we need NIO, and we'll create a final class, echo handler, and it needs to be of type channel inbound handler, or to conform to that protocol at least. And it needs a type alias inbound in, so we need to specify what type of data we're getting in, and we'll have an inbound out, so we need to say what are we sending out, also a byte buffer. And this will become much more useful in the future, because it allows you to send different data types between handlers, and also enrich use much more rich data types than just a byte buffer. So it's possible to, for instance, with a foreshadowing, transform the byte buffer into a sort of string-like command, and then transform the string-like command in a different handler into something, a sort of a sentence that our MUD game understands, and then use a handler to transform that one, for instance, into a response back to our client. Okay, so we have our types defined. Now we need to add this method, channel read. This one is called when ever data is received, and because our inbound type and our outbound type are the same, and we just want to echo back everything we receive, what we're going to do, we're just going to take a context and write and flush back everything we receive, and we don't need a promise here, because this is there's no issue doing this synchronously. What you might notice is when you try and run the application, or when you try and stop it, it's unable to kill the application completely, and it will give an error message the next time you start. We will fix this in the future, but for now we will simply kill the application. Yeah. So we need to make sure that we're killing the one ones that are left. So, and now it should work. So we're still listening on the port. We can still telnet to our local host, and nothing is happening. Because although we defined an echo handler, we didn't add it to the pipeline. So let's give it another go. So we're getting back whatever we type in. Cool. Let's make it a bit more interesting, and this will be the final step for today. Is what I want to do is I want to have the text echoed back in a different color. That way it's much easier to understand what was it that the player typed and the response from the server. And that requires a bit of changing the working with these data types and transforming them into other ones, because these are byte buffers, and to add color into them we need to introduce ANSI escape codes. And that easiest way to do is to have somewhere have a string, so something the player typed, and then let's say we want to make it green. We include something before it and after it, and these will be the ANSI escape codes, and these can be, it looks like a bit of magic, but don't worry, these can be looked up online, fortunately. So what we need to do is we need to put in a code before, and we need to put in the codes after to reset the color to white, otherwise the next thing the player will type will also be in green. So we set it, apparently this is color 32M is color green, and 0M is setting it back to default, or getting rid of all the formatting. So now we have a green string, but this string, of course, you want to be what was sent by the data. So what we can do is we can unwrap the data that we received. So now we have the buffer itself, and we can get a string from this buffer, and we'll start writing at 0, and we'll just get everything that we can read, so all the readable bytes. This returns an optional. If for something reason it doesn't succeed, then we'll just default to an empty string. So we now have our string. Can do a bit of print debugging and say received string, to check that it's really working. So now we have a string value here. We create a green string here, and we can also print out this one. Now we need to make sure that this is the one that was sending back. What we need to do is we need to create a new buffer, and this is also where the allocator that we discussed earlier comes into place. We need a buffer of size at least large enough to contain the entire green string. We now have a buffer, but it's still empty. It's only the correct size. So what we then need to do is write our string into it, and we now have the string inside the buffer in the correct format. Then we need to send this one. Need to send out this one, and we'll use that using the wrap inbound out method, and we'll wrap the out buffer again without a promise, because this is the last step we do. So we'll just make it synchronous. if everything went well, everything the player types is in default terminal color, but what computer echoes back will be in green. So let's stop this and let's quickly get rid of these debug print things. So that's it for now. So we have a very simple pipeline, and that echo is back what a person types in a different color. Might not seem much yet, but this is a really good start. The next episode, what we're going to do is we're going to set up the basic pipeline that this game will use to receive information from players and send back information to them, and implement the first command that they can give to the system, and have the system respond to it. So that's all for now. Thanks very much and have a good day.